Hi everyone, Miss Besega here, and we're taking a look at the Unit 10 review packet. Now, if you haven't used the front page in this way before, what I suggest is as you go through the review packet, go through and start checking off the topics you feel comfortable with. So for instance, if you know that white light is made up of a combination of all the wavelengths, you would put a check next to that. If you feel like you can describe how wavelength, screen distance, and slit spacing affect the space between bright spots for a double slit or diffraction grating, check it off. Okay? For Thursday's test, you're going to be able to use these sets of equations. You should be able to calculate using the wave speed. Actually, a good addition here, you should still be able to calculate speed in general using the distance divided by time, the speed of light in the vacuum, and the index of refraction. All of those calculate speed. You should be able to use Snell's law to calculate either missing angles or missing indices, and use the different distance ratios in the double slit / diffraction grating equation to find the space between the bright spots of light. So imagine these are my bright spots of light, and we're trying to find the distance y between them. So go through with the equations and make sure you know what each is used for. Make sure for each of the vocab words you can look at it and say like, okay, fiber optic cable, I know what those are used for. Check. Let's look at the different equations. We know that wavelength shows up in at least 3 of them. So let's take a look at the multiple choice. Since we just one of them makes sense. Only the wave equation is trying to relate speed, frequency, and wavelength. And we know the speed of a microwave is 3 times 10 to the 8th meters per second. So to calculate its wavelength, I would divide by its frequency. 3 cancels out on both sides. 10 to the 8th divided by 10 to the 9th gives me C, wavelength. My bad. The reason you can calculate that is because if you know the wavelength, the frequency is calculable, because the speed of wave is the same in a vacuum for all electromagnetic waves. Right? We just use 3 times 10 to the 8th for microwave, but I could use this for any type of wave, at least electromagnetic wave. The portion of the electromagnetic spectrum felt as heat is infrared. In addition to knowing the 7 sections of the electromagnetic spectrum in order from least frequency, least energy to greatest frequency, greatest energy, be prepared to be familiar with some of the basic uses of each type of wave. So now we're on to 2 questions about reflection. Reflection is when light hits a medium, or actually any wave hits a medium, and bounces off into the original medium. In this case, angle of reflection is defined as the angle touching the normal line. So this is actually a 40-degree incident angle, giving me a 40-degree reflected angle. So this is 40 degrees, not 50 degrees. Now be careful there, because a lot of people will just say, well, 50 was in the diagram, isn't it angle in is equal to angle out? No, it's defined as the angle that's touching the normal line. So if a light ray strikes a flat mirror at an angle of 14 degrees from the normal, then the angle of reflection should also be 14 degrees. And it's from the normal line, not the mirror surface. So reflection is a wave property that happens with light and sound and all sorts of other waves. Refraction is another wave property. A wave is refracted when it goes from one medium to a different medium and changes speed. Incidentally, wavelength and angle change as a result of the speed change, but frequency doesn't change, so we know it can't be A. It doesn't change. And actually, both angle and wavelength change because velocity changes. The velocity change causes the change in direction and change in wavelength. The reason you can calculate. So when a light moves from air into glass, it's going to change its direction. So let's draw this out. It's going from air into glass at an angle. It would have gone this path. But it's going to bend. And it bends because the glass is denser than air and has a larger index of refraction. Since glass is the slower medium, it'll have the slimmer angle. And so in this case, this light bent towards the normal line in the glass. Now 8, if you notice, is just the opposite question. This is light going from a slow material, water, into air. As a result, it bends from its original path, but this time it bends away from the normal line, making a fatter angle in the faster material, and so it bends away from the normal line. 8 is B. In order for something to be observed, like, let's say I have a glass sitting on the table, right? And the glass is filled with water and the ice cubes are in it. The reason we can see those 3 transparent objects, the glass, the water, and the ice cube, is all 3 have a different index of refraction than the air around it. But if I did something tricky, like putting a bunch of Orbeez into the water, Orbeez have the same index of refraction as the water, and so they don't actually bend the light around it. And so you would see no edge here. And since you see no edge, and it's a transparent material, we can't see the Orbeez at all. Okay, this is just a straight dispersion question. Dispersion is caused because different wavelengths of light travel at slightly different speeds in a medium, and as a result, the light waves spread out. So this is your prism picture, where white light goes in, and the different colors of light, red bends a little bit less than blue, so red ends up out here, blue ends out here, and you end up with rainbowing effects. Dispersion is when white light breaks up into its components as a result of changing speed when it gets to a new material. So 10, 11, and 12 are all just vocab questions. 11 is asking for which of the wave behaviors occurs when something bends through a single narrow slit. That's diffraction. And notice when it bends, it actually spreads out to fill a room or a space. It spreads out in all directions. So think to yourself, this is why we can hear people moving around in the hallway when they're being really loud, right? Because the sound travels through the walls through the little tiny holes and spreads out to fill the room. 12 is tricky because this is diffraction. Because the wave fronts are going through these openings here, there is diffraction, but diffraction doesn't cause the alternating light and dark bands. That is interference. In this case, I would get a bright red spot. If this was a red wave, I'd get a bright red spot here, because that's where the crest meets crest and trough meets trough. I get bright spots here. Following any of these intersections, let's say this one over here, I'd get a bright spot here, bright spot here. Interference, crest meets crest, trough meets trough. That's the 2 waves interfering with each other to make bright spots. Sections of large amplitude. So then we switch over to our atomic energy states and how those can be used to create light. So let's say I have a bunch of electrons, and they're sitting here in the n=4 state. Every time the electron loses potential energy, it emits a light wave. So it could fall from 6 to 5, and that would emit a low energy light wave, whose energy is 1 electron volt, because that's the difference in energy levels. Let's say one fell from 4 to 2, or energy state 4 to 2, that emits a light wave with 3 electron volts of energy. Or it could fall all the way to the ground, and this would have the most energy. So I'm going to draw it with a high energy color, blue. This would have 6 electron volts of energy. So I see that 1, 3, and 6 are allowed energy transitions, but I could also do things like this. When it goes from 5 to 3, it emits a 2 electron volt energy. And the only one that I can't find anywhere on this sheet is a 4. There's no combination of lines that I can make. Here's my 5 in case you missed it. There's no way I can make a 4 electron volt wave. There's no combinations of energy states because the energy states are quantized. I can go to the different energy states from 1 to 2, but I can't go any fraction in between. So the photon with the longest wavelength will be the photon with the least energy. The one with the least energy is from 4 to 3. And if you have trouble thinking of this relationship, it does show up in the photon energy equation, where Hc on top is a constant. Therefore, wavelength and energy are inversely related. Having a small wavelength means a large energy, so having a long wavelength means a low energy. In addition to knowing the 7 sections of the electromagnetic spectrum, you should also know the 7 colors of light. The one with the greatest change in energy of the atom would be violet, because violet light has a higher frequency and higher energy than the other colors in Roy G. Biv. So, diffraction, interference, refraction, and reflection are all wave properties. The one particle property is the photoelectric effect. And this is because, in this case, when a wave hits an atom, think of it as like colliding like a billiard ball. It knocks out an electron. So if we treat this like a collision, then particles can collide with particles. So 17 is also photoelectric effect. If the frequency doubles, what observation would you expect to see? Monochromatic means one color of light, so imagine I have like red light, right? Falls on a surface of a metal, and electrons come off. If I increase the frequency, then that means this photon that comes in has more energy. So that electron that comes out should have more kinetic energy. It doesn't change the number of electrons, and it doesn't change the number of photons. The photon kinetic energy doesn't change because there's no emitted photons. That's not a thing. All right. Electrons are being emitted, and their kinetic energy increases. So, if we treat the electromagnetic spectrum as a continuous list of waves from radio to gamma, there's no sharp distinction between the different types of waves. We only distinguish them by having predefined sets of wavelengths. And what I mean by that is when we're looking at the electromagnetic spectrum, some human scientists said we should call radio waves everything from this wavelength to this wavelength. It's arbitrary. It was defined by a person. So those definitions of bands that were defined by people were radio, microwave, infrared, visible, ultraviolet because it's above violet, just like infrared is below red on our Roy G. Biv over here, X-ray, gamma. Gamma has the highest frequency and highest energy. The longest wavelength is radio. Radio would be long wavelength, but low frequency, low energy. So number 19 deals with a critical angle. This question's asking what behavior happens below and above 45 degrees. For all angles below critical angle, you just get regular refraction. So I'm going to draw this in red. Okay? You get regular refraction. Everything below 45 degrees, the light wave moves from one medium to the next. It just does regular refraction. Notice that in the faster material, it has the fatter angle. In the slower material, it has the slimmer angle. So at 45 degrees, or sorry, less than 45 degrees, we get regular refraction. At equal to 45 degrees, I'm going to draw this somewhere else so we can see it more clearly. And at greater than 45 degrees, then we either get the critical angle. That's when light ray would come in at 45 degrees and go exactly along this medium boundary. So it does not reflect or refract. But above 45 degrees, this is where you get total internal reflection. Let's make this larger than 45. Total internal reflection does obey the law of reflection here. And this is how a fiber optic cable works. Light would get trapped in this high density material, but reflect off each boundary, allowing it to travel down the tube. So, one picture we have is emission spectrum versus absorption spectrum. And it's easy to tell which mixtures are inside a gas. So in this case, in my unknown sample, I know element A can't be in it. These two lines in A don't show up in the unknown, so A is not it. Let's check B. These two lines, which I'll do in red, these two lines in B do show up in the unknown sample. So I'm not color coding here, so don't be mad. Element C might be in it because element C has 1, 2, 3, 8, all of these lines matching up. So it looks like element B and C are in it, but D is not because this line doesn't show up in the sample. Element D cannot be part of that mixture. And just to be clear, since someone asked yesterday. So now we're back. We know the difference between absorption and emission, and since this is supposed to be an emission spectrum here, these would be dark lines or a dark band, and we're imagining just a few bright stripes of light, some that correspond to the elements in B, some that correspond to the elements in C, or the lines in C, 3, 4, and so only B and C are in this mixture. Great, so photoelectric effect. This is a short answer question, and in this case, I have two trials of a photoelectric effect experiment. They're both irradiated with the same frequency of light, but they don't result in the same kinetic energy at the end. Remember, electrons all have the same mass, right? So if B has more kinetic energy at the end, but they both had the same photon energy at the beginning, then A and B must be different metals. Think about it like this. They have the same energy of photon at the beginning, and different kinetic energies of electrons at the end. And the only way you can make that work is if they have different work functions. If they have different work functions, then they must be different metals. Different work functions, that must mean that these are different metals than each other. The difference between absorption and emission spectrum is kind of hard to draw if we're only doing black and white. Notice that for the same hydrogen atom, the absorption and emission spectra both have vertical lines at the same place. Each of those lines corresponds to one energy level. In this case, the red line corresponded to an electron falling from the n equals 3 to the n equals 2 energy state, whereas the teal line was from the n equals 4 to the n equals 2 energy state. So those lines should match up. Absorption, think of this as like the gas is absorbing some of the energy out of the continuous spectrum. So it has dark lines where each of those energy levels are. Whereas an emission spectra is when I have a superheated hydrogen gas. Think of like that rotary demo we did in class with the gases of different colors. We take that gas, get it really, really, really hot, and it would only emit those 3 colors or 4 colors. And we could tell different gases apart because different gases have different energy signatures. So if you're stuck on the difference between absorption and emission spectrum, absorption spectra are sometimes called dark line spectra, and emission spectra are sometimes called bright line spectra. Okay, so for these, I'm going to write a bunch really super quickly, and I would suggest if you want to look at this more closely, check the answer key. Right? Because in this case, these are all just calculations, and at this point in the year, you should be very good at being able to identify problems, identify the calculations that go with them, substitute and solve. So for instance, 22A, we have a frequency, and we want to find a wavelength. The equation that has both frequency and wavelength is the wave equation. So I would use the speed of light plus the frequency is 92.5 mega, so that's 10 to the 6th hertz, and divide to get the wavelength. Answer! Great. Similarly, B, I'm trying to relate distance and time knowing speed. So I know I'm going to be using the distance and time equation. One tricky thing for 22B is how far is the moon away from the Earth if it takes 2.6 seconds total there and back again. So I'm actually going to use the half time. Just t is equal to 1.3 seconds, so I just get the distance from Earth to the moon. So in this case, the distance would be 3 times 10 to the 8th times 1.3 seconds, and that gets 3.9 times 10 to the 8th meters. The speed of light in an emerald, in this case, I'm trying to find the speed of light in a material, so I know I'm using the V is C over N, where C is 3 times 10 to the 8th, and N is the 1.57. And bam, answer. Similarly, I'm trying to find out a material, and I'm going to do that by solving for index. Same equation, solve for N. The speed is 2.29 times 10 to the 8th. C is 3 times 10 to the 8th. Solve for N. The 10 to the 8ths cancel. Multiply by N on both sides. N is going to be 3 over 2.29, or about 1.3. And maybe I need another decimal place here. 1.31. I can see that is closer to alcohol. Actually, nope, closer to ice. Got it. On the chart. And the material that light travels fastest would be air or a vacuum. Air and vacuum, light travels fastest because it has a low index. And think to yourself like there's very few particles in the way that are absorbing the light and re-emitting it and slowing it down. The materials that travel slowest would be a diamond, because a diamond has a high index. And a diamond is very dense, so many particles in the way. So now let's practice Snell's law. In this case, light is traveling from a fast material to a slower material. Glass is denser than air. It has a high index, whereas air has a low index. So the index will increase and the speed of light will decrease. There's more particles away in the glass than the air, and since there's more particles, the light slows down. That makes the wavelength decrease as well. Because think to yourself for this one, Since frequency stays the same, if the velocity decreases, so must the wavelength. Frequency of light stays the same because, guys, this light is still going to be red when it goes into this new material. So let's draw out this refracted ray. While we're here, we've got the normal line, labeled N. The interface, we have the incident ray. We've got the incident angle, that's that 60 degrees incident angle. We've got the 30 degrees refracted angle. And so I can calculate the index of refraction using Snell's law. And actually, if you check my drawing, notice that the angle of refraction decreases. It's going from fast to slow. It will be in the slower material. It'll have a slimmer angle, and a slimmer angle, it decreases. So light bends towards the normal line. It doesn't continue along the same path down where it wanted to go. The light wanted to go here. This is the same path where the light wanted to go, and it bends closer towards the normal line, though I see that that word got cut off at the end. So light bends towards the normal line. So let's go use Snell's law. Index of refraction, you should know off the top of your head, is just going to be the 1 for air. I'm not going to make you memorize the other ones. So in this case, 1 sine 60 equals unknown sine 30. Make sure at this point your calculator is in degrees, and make sure you don't just cross the signs out. That's not how sine the function works. So I substitute sine 60 to get 0.866. I substitute sine 30 to get 0.5, divide by 0.5 on both sides, and this gets me an index of refraction of 1.73, which is good, because index of refraction I expect to be between 1 and about 2.5. And finally, the wavelength. I know my wavelength has to become smaller as it goes into the new material. Originally in air, the wavelength was large. And so what I'm actually going to do is I'm going to find the frequency first. 650 nanometers, that's 650 times 10 to the negative 9, means that in air, this would be I want to say 4.6 times 10 to the 14th hertz. It's the same frequency in air as it is in glass. So once that frequency is found in air, I can take the new speed in glass to find the wavelength in glass. So in glass, the speed would be 3 divided by 1.73, which is coincidentally 1.73 times 10 to the 8th meters per second. Find the wavelength, knowing the frequency was 4.6 times 10 to the 14th hertz. Divide on both sides on the same page, and that gives me 3.77 times 10 to the negative 7th meters. And I know that doesn't look right, but that's because we've been doing wavelengths in hundreds of nanometers. So this is 377 nanometers. The wavelength is smaller in glass than it was in air. The wavelength in air was the 650. The wavelength in glass is smaller. Oops. We're getting there, guys. Okay, 24. We're trying to find the thickness of a wire. And I can make this measurement because let's say I take a laser. 640 nanometers is a laser that's red in color. It'll bend around the wire. And that bending around the wire creates interference. Since it bends around the wire, that is diffraction, and the two waves interfere with each other to make patterns of bright and dark. So in this case, it's diffraction because it bends around the wire, and interference because it makes the patterns of light and dark where the two waves interfere with each other. In calculating the thickness of a wire, we're solving using the one, and there's only one, equation here. Since this is a diffraction equation, there's only one equation for diffraction, so we're good. We know how to do this. I notice in the problem they use x instead of y. No big deal. It says the bright spots on the screen are separated by a distance of x. So this is going to be this distance right here, and will be solved using y in the equation. So I'm solving for the thickness of the wire d, so I'll multiply d by both sides. And just substitute all my numbers in meters. Wavelength is 640 times 10 to the negative 9. Length is 0.5. Y is 3 centimeters, which I'm going to want to convert to meters. And that gets me 1.07 times 10 to the negative 5th meters. Now, notice that I can only do this for objects that have a very small width. I can't really do this with like a glass that has a really large diameter, because then those bright spots that I would get would be too close together. You wouldn't be able to see it. It wouldn't do the bending around and diffracting business. Okay, so now I take my green laser instead. The bright lights would then be closer together. And a picture to keep in the top of your head is that if the red lights are this far apart, that's because the red light's wavelength is larger, right? And so if green were in the mix, the central maximum would be in the same spot, right? But green's wavelengths are smaller, so it would be closer in spacing than red. And so you'd get this consistent rainbowing effect where green would always be closer to the center than red, because green has a smaller wavelength than red. I suppose I started answering question D already. If the thickness of the wire were even smaller, so let's take this equation again. If the thickness of the wire were even smaller, that would make y farther apart and more obvious. I can only do this method for very small objects because that's the only time I get spacing large enough to be visible. They're farther apart because it's an inverse relationship. Ooh, this is going to be tricky. I don't know if I can clearly draw on this, but we're going to try, okay? So let's say I take my red light, and it goes through the two little openings over here, and it diffracts, meaning it bends and goes through the two openings and fills the space on the other side, spreads out in all directions. I'm trying to do an interference pattern. So crest meets up with crest. Those positions. The next one out would be here. And you know what? If you print this out, you'll get like straight, nice, pretty lines, better than mine. And that constructive interference leads to bright spots. These are my antinodal lines. Same thing on the other side, but symmetrical. Okay. So, and darker and easy to see now. The antinodal lines represent two waves. Crest meets up with crest. This would be constructive interference. The crest meets up with crest, the trough meets up with trough, and so you get a wave that has a larger amplitude than it did before. Now, nodal lines are the opposite, so I'm going to draw these a little bit different. They will be right between your antinodal lines. So I suggest draw your antinode lines first. Nodal lines will be right in between them. And the nodal lines are where destructive interference is occurring, where a crest meets up with trough. And so then I get darker spots. It says label the screen where the bright spots / maxima would occur. Bright spots labeled. The dark spots would be all of this area in between. Dark, dark. So dark, sometimes you'll hear me call these minima because minimum brightness. And the bright spots you will sometimes hear me call maxima because those are the maximum brightness. And just like in the last problem, if the wavelength were increased, like it were made an infrared in this case, longer waves would have larger spacing. Because look at our equation here. If wavelength gets bigger, the distance between the bright spots gets bigger. Direct relationship. 26. Energy level diagram. It says draw all 3 energy levels. Easy peasy. I can do that. I can even color code that. What do you guys think? Okay, so let's say I take blue will be the highest energy. This will be an electron that just falls from second to ground. Then let's say I'm going to take my 2 low energy ones. This would be 1.5 electron volts and 1.1 electron volts. And I'm getting this by just subtracting the difference in energy between these two. And 3 would be 2.6. There we go. And it says calculate the wavelength of each of the jumps. I'm going to do this once so that you guys don't have to see me do it 3 times. Okay. We want to get wavelength knowing energy. So let's use an equation with wavelength and energy. I'm going to use 1240 for H times C, and since this is already in units of electron volts times nanometers, I can just leave everything in nanometers. My answer will come out in nanometers, which is great. Let's substitute in just for the highest energy jump. That's an energy of 2.6 electron volts. So in this case, I'm going to multiply by wavelength on both sides. Wavelength would equal 1,240 over 2.6. Units are going to come out in nanometers, thankfully. See, like electron volts just cancel out there. And that gets us 476 nanometers, which is bluish. Okay, so I'm going to take a second. I'll get you the other 2 numbers so we can keep going. And that's curious. My other 2 numbers, when I do the 1240 divided by 1.1 and 1240 divided by 1.5, both of these wavelengths are outside the visible spectrum. Since they have the longer wavelengths, these must be infrared wavelengths. And remember, I got these by doing the 1240 divided by 1.1 and 1.5. So my lowest energy jump then is going to be this guy. To get its frequency, I'm going to use an energy equation that relates energy and frequency and solve for F. In this case, I know the energy is 1.1. H is a universal constant I'll be able to look up if I need it. It's 4.14 times 10 to the negative 15th electron volts seconds. And that means my electron volts unit cancels, and my frequency ends up being whatever 1.1 divided by Planck's constant is. Notice that I should be getting really big frequencies here. In this case, this is something like 2.66 times 10 to the 14th hertz. So when I go draw the emission spectrum, this is going to be a pretty boring one. Only one of those colors shows up in this range at all.
The 476 is going to be right around here-ish. But the other two are way out here in the infrared part of the spectrum. They are not visible to humans. So let's say that I find this atom, and I'm looking at a galaxy that's far, far away, and I see this shade of blue, this specific spectral line, but I see it slightly shifted to the right. I see it with the same set of wavelengths, but instead of being at 476, let's say it's maybe at, I don't know, 495? We call this a red shift because it's shifting that same one frequency towards the red part of the spectrum and away from the blue part of the spectrum. And red shifts means longer wavelengths. Longer wavelengths means that that galaxy must be moving away from us. Picture the Doppler effect picture in the back of your head. Remember with the Doppler effect? If I have a galaxy that's moving away from us, it has long wavelengths. If that galaxy is moving away from us, the wavelengths are stretched out. They're here. They're much bigger. The wavelengths are long because it's moving away. So we can actually use light from stars to determine whether the galaxies are moving away from us or towards us. And guys, in a few billion years, it's going to get real lonely in here. All of the other galaxies, except for the ones in our local group, are moving away from us. So, the last two problems are the ones I wanted you to try on Tuesday with the photoelectric effect. For 27, we're graphing. So, you don't need to watch me graph. Pause. Yay! I plotted some points! Let's figure out what these points mean. We plot the points. It kind of got cut off here, but this is, your 10 to the negative, or 10 to the positive 14 hertz. So this is frequency on this axis, kinetic energy on the y. There's where my points, and I'm going to draw a best fit line that kind of tries to make it over here. Okay. So what this means, and I'm sorry that my picture is awful. You'll live. What this means is the cutoff frequency is my x-intercept. It's the point at which I have just enough energy for the electrons to escape the metal, but not enough energy to send them shooting off into space or whatever. So cutoff frequency for the metal, I'm just going to read right off the x-axis, looks like 4.5 times 10 to the 14th hertz. The work function, choices here. You can try to extrapolate backwards and find the y-intercept, which would be somewhere down here-ish. But given the choice, I don't think that will work very well. So what I'm going to do instead is, if you were in math class, guys, let's try this. Pick any point. Okay? Pick any point. We want to take the energy of the photon and find the work function given the kinetic energy. So we can do that this way. It's like solving for the y-intercept by plugging any point into y equals mx plus b. So I'm just going to pick an easy to work with one, the very first point. It's light frequency. I can get its energy by using h times f. I'm going to solve for phi. And I have its kinetic energy already. It was given to me, so I can do that. Give me 1 second to sub. So I substitute in our value for h, which is a universal constant. Look it up. The frequency, which was given in the table over there, and the kinetic energy also given in the table. This gives a work function of 1.97 electron volts. This number makes sense because if I remember all the other ones I've worked with in charts before, those numbers were around like 2 to 5 electron volts. So I know I'm in the right range. Now, if a 3 times 10 to the 14th hertz metal Photon strikes the metal. I've got this, guys, I swear. Then it shows up here. How much kinetic energy does it have? 0. No kinetic energy because no electron emitted. It doesn't have enough energy to get out of that electric well. It doesn't have enough energy to escape the metal, and it doesn't have a frequency that's higher than cutoff. It has 3 less than 4.5, so it doesn't have enough frequency or energy to cause an electron to be emitted. However, 10 times 10 to the 14th, though, that's a lot more energy. That's this next data point right here. And we can either estimate the next data point by just like extrapolate this, like 1.7-ish. But let's be precise. It says calculate, so we might as well. We'll take our energy of a photon. That's what we're trying to solve for. Or sorry, our energy kinetic is what we're trying to solve for. We know the work function. We're going to solve for this kinetic energy. The energy of the photon would be h times f. The work function, we're going to use the 1.97 from earlier and solve for Ke. Okay, so substituting in h, the universal constant, times the frequency that was given in the problem. Notice that my powers of 10 cancel here. 10 to the 15th cancels 10 times 10 to the 14th. And this is math I can almost do in my head. Because it's 4.14 is equal to 1.97 plus K. Subtract to self K. Last problem. Photoelectric effects still. This is one I wanted you to practice on Tuesday. We're going to get real good at calculating the incident energy of photons. I feel like we just did this a whole bunch of times. All right. In both of these problems, we're taking Planck's constant. It's a constant. You can look them up. And multiplying by the frequency. 1.8 times 10 to the 15 hertz. The 15s cancel. So 1.8 times 4.14. And similarly, in this case, the 15s are also going to cancel, so I'm not even going to write them. 4.4 times 2.6. And that gives me energies of 7.45 and 10.76 electron volts respectively. So which trial will have faster electrons? They're both the same nickel disk. But, well, trial B has more energy than A, so B has faster electrons. In fact, we can actually calculate that. So let's do that first. To calculate the energy of the electrons, we know that the energy of the photon is equal to the work function times or plus kinetic energy. So this is just subtraction. The light put in 7.45 electron volts. It took 5.1 of those electron volts to escape from the atom, so the kinetic energy in B would just be subtracting. So there's 2.35 electron volts for case A. The kinetic energy in case B would be taking the energy in from the light, subtracting the work function, and so that's about 5 or so electron volts. In part D, leaving B to definitely have the faster energy because it has more kinetic energy. But the one with more electrons is A. The one with more electrons is A because intensity is proportional to how many electrons hit. A has more intensity, and the more intense the light is, the more electrons there are. So think to yourself, A is a lot of electrons, but they're slow. B might only have a few electrons, but they are fast, speedy electrons. So if I want to make the best solar panel ever, I want to make this as functional as possible. So I would increase the frequency of light, increase the intensity of light. I suppose if you really wanted to, you could increase the surface area. That might help, right? Think you have a larger surface area, so there's more electrons being knocked out. But the other one we had talked about was make a metal with the smallest possible work function. The easier it is for electrons to escape, the easier it is for us to harness their energy. So, best of luck on your exam on Thursday, and have a great spring break, guys. Bye.